The recording. So it's a pleasure to have Dan Carney. He's just moving to Berkeley, though he's physically present in Vancouver right now. He'll be telling us about gravitational direct detection of dark matter. So please go ahead.
Yeah, hi everybody, and thanks for the invitation. So I sent an abstract, and it said something about overview of mechanical sensing, blah blah blah, because I sort of always use that abstract. But then I was mentioning that I was giving this talk to someone, and they said, you know, this is just a group full of these really hardcore Russians who are going to just grill you the whole time. And I was thinking, you know, I took 2 years of field theory with Vadim Kaplanovsky in grad school and survived that, and I'm kind of nostalgic. So I'm kind of looking forward to getting grilled. So I decided I would give a talk on something I think that's a good two-way discussion topic. So this is a very light talk on just specifically this gravitational detection of dark matter problem, which is a little crazy. And you know, I'm very much looking forward to some feedback during the talk. I know Maxime, I hope Maxime Paslav's in the audience because I know he's thought about this a bit. So this started.
Yes, I had a paper in 2016. Sorry, I was muted.
Yeah, good. Yeah, so this started for me with this paper we wrote in 2 years ago now, I guess, with Gordon. Jake was my boss at Maryland, so he's like a real quantum sensing dude, and so he's his student. And then it sort of spawned this whole monster of a research program, and there's a lot of people involved now. So I rate some of them. These are sort of the senior people. So the top line are experimentalists, the bottom line are theorists, and the ... means a whole lot of other people who are younger typically. So I'm not a particle physicist really by training. I'm more of like a string theorist by training. And so I hadn't not thought about dark matter a great deal until this project happened. So here's my take on dark matter. You know, if dark matter exists, and Gordon would not let me write this phrase in the paper, he said dark matter exists and therefore blah blah blah. So okay, my personal take, okay, there's a lot of evidence, so let's say it exists. The only thing you know about it for sure is that it's going to gravitate. You also, roughly speaking, know how much there is, you know, to within an order of magnitude, let's say. Pretty much what you know is that there's about a proton mass per cubic centimeter. And so, you know, if you wanted to detect it through this only gravitational coupling, it sounds completely crazy. If you want to detect it locally in particular. So what this talk is going to be about is this idea that, like, well, okay, maybe it is crazy. You know, lots of people have made estimates and tried to think of how to do this. And typically a sane person would just throw away the paper after you make the estimate because it looks nuts. And all we're trying to propose here is like a path towards maybe doing this in some sort of niche parts of parameter space, in particular with sort of heavy dark matter that's heavy enough you can maybe detect it, but light enough that you'll actually get a non-negligible flux in a terrestrial experiment. So this is my cartoon of how I would like you to sort of think about this talk. So this is a picture of Kip Thorne, and he's talking to, well, this is Bryce DeWitt in the back, and Yuval Ne'eman, and I don't actually know who the back of this person is. And I think this is at Les Houches. And so I'm just sort of imagining, you know, where Kip Thorne, maybe not in terms of greatness, but at least in terms of how hard our problem is, talking in the 70s about LIGO. So, you know, I say, I have to just detect vacuum fluctuations of some totally macroscopic objects that I put, you know, kilometers apart, and like, well, if we could do this, we could detect gravitational waves, you know, assuming they even exist in that mass range, which was not known at the time. We're kind of sitting at that same level. So we have a proposal for how you might do something. It needs some substantial technological progress to get there. And we also don't know for sure that there would be a signal. So we can't detect all dark matter. It's only certain masses, and so who knows if it's that mass. So nevertheless, though, it's just sort of like a fun thing to think about. And even if, you know, it winds up not working, there's a ton of interesting technological questions between here and the goal, just like in LIGO. So what I'll do is I'll sort of outline the detection problem. This is the easiest thing on the planet. And then I'll sort of talk about the proposal we made. So how to use an array of detectors. And then the real meat of the talk is about the noise. So how do I estimate and think about the noise in the kind of detectors we're going to have in mind. And then I'll talk about what's going on experimentally and some questions we're working on now. Okay, so here's the basic idea, and we were not the first people to think about this. So this really is the whole scheme in a way. So the picture here is just this black blob is some piece of dark matter. It's going to fly through your lab at, let's assume, typical virialized velocity. And then what you're going to put to look for this is some kind of mechanical detector. So this is my cartoon of something like one arm of LIGO, for example. So this is a mirror that's suspended on some fiber. So the mirror can swing with some frequency. I put it in, I make a cavity. So one side of the cavity is this mirror. The other side is a fixed mirror over here, which we draw bent for various reasons. And what you do is you monitor the position of the mirror, just like LIGO does. Okay, you send laser light into this cavity. The light reflects off of the movable mirror, comes back out the cavity, and then you measure it. And what you measure actually is you measure the distance between the two sides of the cavity. And the way you do that is that distance is proportional to the phase shift picked up by the light as it reflects off this mirror and comes back out. So what you actually do is you have a little interferometer out here, usually a homodyne interferometer. You read out the phase of the light coming out of the cavity as a time series. And from that information, you get the position of the mirror relative to the fixed mirror as a time series. If you know the,
I'm sorry. So it is interference between moving mirror and fixed mirror light light or what is observed.
Sorry, what is what?
No, I mean it is interference of light which reflected from moving mirror in relatively to fixed mirror. What kind of interference?
Yeah, that's what. So this little box here, I don't actually draw. There's a local oscillator here, so you actually inject some other known frequency of light, and you look for interference between that known light and the output of the cavity.
I see. So then there is no light reflection from a fixed mirror, right? So just this one. No, it's what I'm wondering, because you can also compare, this kind of to see even just a difference between fixed and this mirror. I thought that it might be light reflected from a fixed mirror. No, I see. I got it.
But this is conceptual, right? In some sense, this little box can also be a splitter. So I can split out one laser and get reflected by the mirror and by this pendulum and reflect back.
Mm-hmm.
I think it's conceptual in some sense. There's many difference you can do, reduce various systematics.
Okay.
Yeah, that's right.
So can I also just ask a basic question here? Because when this looks like LIGO, so when a gravity wave comes through, you change the distance, the overall distance here, you get the interference effect. So what's the individual dark matter particle going to do here? Is it going to move the mirror? Sorry, I still missed it.
Yeah, that's good. So it's a bit, okay, good. So this is a difference with LIGO. So as you say, LIGO comes through, it's a long wavelength wave. It'll actually move this entire apparatus. And so there's some subtlety to that.
Exactly.
So here, it's critical that what we're assuming is that this mirror, so the idea is the dark matter comes through, let's say it passes close to this moving mirror, it will move this mirror and not the fixed mirror, sort of speaking. Okay. And so what you see is the differential movement. So it's actually important that, by the equivalence principle, you're looking for the tidal force between these two things, if you want to put it that way.
I see.
Well,
Right.
even for LIGO, you have fairly distant mirrors, right? So you perturb one arm, not the other when it moves. I mean, if it's too far away, then then it pulls on both. But if it passes near one, then you have disturbance.
That's right. Yeah, so this could literally be, and this is, Maxime has looked at this. I mean, this could literally be an arm of LIGO or LISA, for example.
Well, the paper we wrote is a bunch of LIGO people, right? With Rana, who is one of the key players.
So
Okay, thanks.
For the-
Yeah, thanks. Yeah.
okay, good. All right, and just it bears repeating because I think people forget that we're really seriously contemplating this. This is the force we're looking at. So we're looking at this force between this ball and this mirror. Okay, so it's a very weak force. And so that force is actually why I got involved in this problem. I really just think about gravity typically not involving dark matter. And I was interested in these devices. Okay, so there's a lot of devices that are sort of LIGO-ish systems, but they're at various different scales. I'll show you a bunch in a minute, but this one really got me interested. So this is a pendulum. It's in Japan. Nobuyuki Matsumoto is sort of the PI on this work. This is a mirror. This is exactly the cartoon I just showed you. This particular thing is 4 milligrams. Its fundamental frequency of motion is about 4 hertz, which you can drive up to a kilohertz if you want with a laser. And they have systematically improved this thing for years as a force sensor, and it's designed to sense gravitational forces at about millimeter distances. So to put some numbers, and these numbers are useful for the whole talk, if you think about the gravitational force of 2 milligram scale objects placed a millimeter apart, it's about 10 to the negative 17 Newton. And so these kinds of devices have sensitivities now, and there's many systems with even better sensitivity than this. They're quoted as number of newtons per root hertz. So this is 4 orders of magnitude less than this. Okay, so this means if I could integrate for 1 second, I could see something that's 10,000 times weaker than this force. Now, in our problem with the dark matter passing through, you don't have a second to measure, right? The dark matter flies by at 200 kilometers a second. So, now you're actually having to worry about this bandwidth. But nevertheless, I mean, I think this is supposed to be a sort of a sense of why these scales are going to appear and why it's not totally crazy to look for heavy dark matter, where by heavy, I'm going to mean sort of Planck mass-ish, because the Planck mass is, in the ballpark of a milligram. So that's sort of the
I'm sorry, but they already can measure something, maybe not dark matter, but what is a way to kind of verify this, I don't know, device? Do they measure something? I mean, to demonstrate how it works?
Yeah. So there's actually a really beautiful paper by a different group. I don't know, 3 months ago, maybe in Germany, in Marcus Asselmeyer's group, which is literally this thing. So they have one of these kind of sensors. They take another mass on a torsion balance that's also about a milligram. They oscillate the torsion balance, and then you can see it ring up the motion of the sensor.
Yeah, it's what I was asking about. Yeah, thank you.
So yeah, it's demonstrated at this point. So the key there is that, the source that they're looking for is a milligram, and you integrate for like an hour or something. So it's easier in some sense than the dark matter problem.
Right, but it is demonstration of the concept, right?
Yeah, exactly. So good. So yeah, like I said, there's many architectures, and you can kind of imagine doing similar things with all of these things. So I just like to show these pictures for experimentally inclined people. So, I'm showing this suspended mirror, and I'll sort of use that as a prototype through the talk. But there's other things. You can have a mechanical drum head. You can have a levitated bead. You can have these bendable pieces of metal. There's all kinds of systems that are all basically the same category. They're linear, opto, or electromechanics. It's a mechanical degree of freedom coupled to some optical or microwave field, and you read it out interferometrically. Okay, so in terms of this dark matter detection problem, what are sort of the basic scales? So it's pretty easy to understand. So what do you want? So one problem, here are the things. The force is weak, okay? It's G Newton times the mass squared. That's not great. So what do you need? You want a heavy mass, you want a heavy dark matter mass and sensor mass. It's also a 1 over r squared law, right? So you want the dark matter to get as close to your sensor as possible, okay? So great. Okay, so say I want heavy dark matter. Well, what's the problem then? The problem is that the flux of the heavy dark matter will be low. We know the local density of dark matter. If you break it up into big chunks, the number density becomes quite small. And so as a scale here, if I had a meter square area, I can catch about 1 Planck mass dark matter per annum. It's not many, right? So what do I want? I want to make some device where the dark matter will typically get within some small distance from the device. On the other hand, the device has to be kind of big. Okay, so what's the obvious solution? You just put a lot of devices in a box. So you make a big box, you fill it with little devices like these little pendulums, for example. Okay, and now what happens? The dark matter passes through here. It will get close to some track worth of sensors, and then what you're looking for is just a correlated motion of a track of sensors as the dark matter passes through. So you can organize this, right, so that the impact parameter will typically be small. I mean, typically meaning on the track. On the other hand, you can imagine making a large cube of these things so you can actually catch some dark matter. That's the fundamental scaling issues. On a more practical level, if you want, there's also a lot of nice detector things here. So the signal is a correlated track of stuff. There's very few backgrounds. It's very hard to move, a large number of sensors in a track like this. It's also directional, right? You know exactly where the dark matter goes through, and if you're time resolving the thing, fast enough, you even can measure its velocity.
But which way the registration of movement is going on? Now you have many channels, right? Well, how it's measured?
You mean I don't know where it's coming from? How do I do this exactly? Yeah, this is a very good question. So yeah, I'll say some stuff about this, but in some sense it's work in progress still. Let's just say that there's a lot of work from detector physics and also from non-fundamental physics.
No, but you are not having a laser for each pendulum, right? I mean, it's not this way.
That's what you're asking. Oh, so this is a very interesting can of worms. So at the simplest level, let's just imagine that yes, we are. So then, you read out each sensor individually, and then so what you have is some data set, which is like the time series of the force on every single sensor. And now you have to do some scan for this. That's the simplest way to conceptualize this. It also suggests that you wouldn't want to use lasers and pendulums, because how are you going to fit, that many lasers and all this crap?
No, so that's why I'm asking.
So if you want to think like that, then probably you don't want optical readout for something like this. You probably want circuit-based microwave readout. So for example, you can organize this so that the pendula are coupled to a capacitor, and there's a little wire. And so what happens is as the pendulum moves, it will deform the capacitor a little bit, and so you can modify some current coming out, and then it's all fibers.
I see.
That's actually the architecture I'll show later. The key though is that the mathematics of the noise and all that is identical no matter how I think about it. So I like to use the pendulums because people know about LIGO. So yeah, I've already talked about these scales. Okay, fine. So that's really the whole concept for the detector. And okay, sounds great. So this is Ray Weiss saying, what about the noise, man? Like, that's impossible. Okay, so let's talk about noise and how this actually goes down. And this is how I picture noise in the system. It's sort of a minimal amount of noise. The noise here is kind of an interesting problem that is a little understudied, actually. So the reason I say that is because the actual detection problem is very different from the one in LIGO, as we were talking about earlier. It's not detecting a wave, it's not monochromatic, it's an impulse. It's a very fast moving thing which just bangs on your detector and you want to find that. So sort of signal processing language, what you have is a time series in the force, and you have some noisy junk, and then you're hoping to see some spike in an event. And the question is basically, how well can I see the spike over the noise? So this is a little technical, but some people like this, so I put it in here. So what you're going to do, right, is you're going to have this time series for a bunch of detectors, and what you need to do is go through this time series and find these bumps. So there's a sort of a theory of this, and this is how LIGO looks for its waves. It's called matched filtering. What you do is you say, I think I know what shape the signal has in time, and now I scan through with some convolution on that shape. And so this creates an observable which basically looks like 0 if the shape isn't there, and then it peaks when the template you're looking for matches some piece of your data. And you scale it in such a way that you weight the less noisy parts of the data more. So there's this signal to noise ratio you can derive from this. Okay, this is optimal in some sense. And what goes in here is, this is a in frequency domain on new. Okay, this is the signal template that you think you're looking for. The amplitude can be floated, and you're dividing by the noise. So this n of nu I'll use a number of times later. This is a noise power spectrum in the device. So we're assuming you can characterize it very accurately. And what you're doing here is you're just saying, you know, the less noisy parts of the data, I weight them more highly.
But you're, it means that you're implying that you're working not with time function Fourier transform of this time signal, right? Or what?
That's right.
I see.
I mean, I guess you can actually perform the convolution in time or in frequency. It's sort of, let's say it doesn't matter, as long as you have a box that's long enough. But I'll estimate, this is the nice way to calculate it. So I'll show you why, because you can calculate this n of nu function very nicely for these systems. I just want to put this here though, for people who like have seriously thought about detection. I mean, this is how we estimate signal to noise in this device. So this means a signal to noise, this is not like, what the signal to noise means is, I pick a track, I ask, is this bump on my data in the track? And then I ask how well can I resolve that bump above the noise on the track? What is the noise? This is my bread and butter work now. So what is the noise in this device? So there's a lot here. Okay. The idea and what I'm going to talk about in the rest of this is, there's a lot of technical noise in all these devices. There's like stray fields and all kinds of horrible things in a real device. With a decent sufficiently good experimentalist, they can get rid of all of this. And this is now a standard thing. And you enter a regime which your device becomes limited by two things: thermal noise and quantum mechanical noise. Thermal noise, I think everybody's familiar with. You know, you have a suspended pendulum. The pendulum has a temperature. It will cause the mirror to move. It's a mess. Okay, but you're just, in some sense, always going to have that. There's no actual zero temperature device. That's one thing. There's another problem though, which is maybe less appreciated. So this is called quantum measurement noise. This is a whole thing. Quantum measurement noise has to do with the Heisenberg uncertainty principle. So I'll explain it in a minute, but let me just say that, for example, advanced LIGO is limited by this. Quantum measurement noise is the dominant problem in advanced LIGO now. So what I'm going to talk about now is, let's assume that these are my dominant noise channels, and how well can I do? So a little more mathematically, I'm just giving you a plot here of what these noise power spectrum kind of things look like. Okay, so this is as a function of frequency. I'm plotting the typical amount of noise in the force variable as a function of bandwidth. And there's a bunch of contributions. So there's some thermal contribution, which is this green line that's flat in frequency. So this is just white noise. And then there are these two curves, shot noise and back action. And these are the quantum measurement noise terms. So the shot noise is saying, I send in a laser, the laser has random vacuum fluctuations around the coherent drive. Okay, that is a shot noise. When I read it out, it's going to cause some root n problems. On the other hand, there's this back action noise, and this has to do with the fact that the laser has random radiation pressure exerted on the mirror. So that will cause the mirror to move around, which will then be subsequently, show back up in my readout. As I send the next light pulses in, those get reflected off of this now randomly moving mirror.
But in this way, it is, how to say, it is a noise due to kind of photonic nature of the light, or it's not quantum noise of kind of massive body itself, right? Because what you are describing, it is kind of, I mean, I believe that it is about light, or I'm wrong.
No, you're exactly right. So this is the noise caused by the probe, the light.
Yeah, I see.
So that's why it's called measurement noise. It's sort of like, you can't get around this because you have to measure with something, and the thing will always have noise.
I see. Because the massive body itself probably doesn't produce much of noise, right? I mean, I see. Okay.
That's right. So in this curve, in fact, you can see that. So the massive bodies noise, if you want, is this thermal line. That's saying like the mirror itself has some thermal fluctuations.
Yeah.
And in this plot, and this is like some plot with a milligram detector and a hertz and the same parameters, the thermal noise is subdominant to all of this quantum measurement stuff, right? So this is exactly the scenario you're describing.
So you'll be dominated by shot noise, you're saying?
Yeah, in this particular example.
But when you mentioned this capacity measurement, whatever, it's a different nature, right? So it's a different kind of noise there.
So yes, in the physical way it manifests. However, in fact, mathematically, it's the same thing. And in a way, it's the same thing physically. So with the capacitive measurement, what you have now is you have a current. You shoot a current into the system. The current has a shot noise. And also the current has random fluctuations, which will cause the capacitor to deform, which will cause the mirror to move. And that's the back action. So you're kind of always going to find these things. So in that sense, they're quite universal. Okay, well, I'll have a slide about some more details about the measurement noise. It's a nice topic. Let me, before I do that though, say what sort of the punchline for the dark matter problem is going to be. This is sort of the bold claim here. So the claim is, suppose I can get to the thermal noise floor. So this is, not what is going on in this picture. Here, the thermal noise is lower than the measurement noise. Suppose the thermal noise, we got the measurement noise down low enough, right? If I only had to deal with the thermal noise, the statement is basically that you can detect Planck scale dark matter through its gravitational force if it passes about 1 millimeter from a detector. That's what this SNR estimate is. So there's all these parameters. This is, the impulse delivered by the passing dark matter up here. B is the impact parameter. And I'm just comparing it to the thermal noise. So you can see there's an M, KB, K Boltzmann temperature. This is just the thermal fluctuations, thermal fluctuations hitting the mirror. Okay. There's a factor of the quality of the mirror. So for a very low damped mirror, the thermal noise is less. It acts less in a given amount of time. And if you put in some numbers with, with a good high quality mirror, like the Japanese groups that I showed earlier, I think that's the number I used here. And you put the temperature in a dilution refrigerator, so very low temperature, this is 10 millikelvin. And what you can work out is that the signal to noise is actually sort of order 1. So this is supposed to be a good result. It may look weird to say there's a 0.5. Okay, you might think this means it's not detectable, but to me, this means I just need 10 detectors and I'm good. Okay. So this is an amazing statement, really. This is saying that if a milligram dark matter gets 1 millimeter away from my mirror and passes it at 200 kilometers a second, I can actually see that impulse above thermal noise.
But in your plot, it looks like, let's say that we are collecting, extremely low frequencies, right? With 10 to minus 3, whatever. That there it is, hierarchy is different, right? I mean, in this range. So I'm not sure whether it's practical, but it means that you have a kind of long exposition, right? I mean,
yeah, very good. So let's see here. On this slide, the way to say this is I'm saying now, let's suppose by some quantum tricks that I'll talk about later, I can get the measurement noise curves below the thermal noise. Now the thermal noise is flat in frequency. So actually this formula is just exactly true in that sense. It's you add up the noise, you add up the signal on all the bands, and the signal for this is going to be a flat function up to about 100 megahertz. That's set by the fact that the dark matter comes by at 1 millimeter and 100 kilometers a second. You can make a scale, it's about 100 megahertz. So you just add it all.
That's why in LIGO it's 100 hertz. So in LIGO it's actually in their preferred range.
You're saying this is why LIGO LIGO's.
Well, what I'm saying is that if you take a dark matter and pass it through LIGO, you take the velocity of dark matter divided by the length of the LIGO arm. That's how you arrive to the equivalent frequency, right? And you get to 100 hertz, right? Because the velocity of dark matter is 300 kilometers per second, and the LIGO arm is a few kilometers. So and that's what I assume for impact parameter, that's your sort of 1 over time of the passage, right? Is roughly the optimal frequency. That's
I see.
how I would.
Yeah, but sorry, Maxim, I think LIGO is looking for a wave-like dark matter, not for a particle-like dark matter.
Oh, that's what we did in 2016 to see if you see gravitational strength dark matter, and the answer is no, you can't with LIGO. Or it will be very rare events, right? And yeah, you can. Absolutely you can do that, right? I mean, the question always as a noise, at least in LIGO, it's an optimal equivalent frequency relative to their noise, and if you go to higher masses of dark matter, you can use future LISA style things, yeah. But that's why here it's because of the smallness of the device. Equivalent frequency is probably a megahertz, right?
That's right.
Yeah.
Yeah, exactly. We're assuming, yeah, millimeter to centimeter scale device, so the flyby time is much faster than if you were saying the impact parameter is the size of LIGO. Which,
right,
yeah.
and of course for LIGO, then the optimal masses are going to be not milligrams. You're never going to be sensitive to milligrams, but more like I forgot a kilo or of some sort, right?
Yeah. All right. Very good. So good. So from this result, the statement is, with these at these scales, if I could do thermally limited detection, I can detect, Planck mass to milligram scale dark matter. That's roughly the punchline here. And so then the big caveat is I'm saying that I can get to the thermal noise floor, but in the plot, the measurement noise is above the thermal noise. So, how do I actually achieve this? So now you have to actually dig into what the hell this measurement noise stuff is, okay, and really quantum mechanically what it is. So this is Heisenberg explaining this. So this is just to show some equations, just to prove that we're not just making order of magnitude estimates here, which I'm going to do for the rest of the talk. But this is how you actually look at this stuff. So this is the mathematical description of the system I've been going through. To put a little more meat on it, it's basically 2 degrees of freedom coupled to a quantum field. Okay, so the 2 degrees of freedom are the fundamental mode of the cavity, which I give variables x and y. This is they call them the amplitude and phase quadrature. It's just a harmonic oscillator. Then the mirror itself has the degrees of freedom, x and p. Okay, and both of these are quantum mechanical. They have some commutation relation and so forth. They're coupled through this optomechanical coupling. So the position of the mirror is coupled to the amplitude of the, it's coupled to the amplitude of the light mode, okay, through some coupling. And this coupling G is tunable in the sense that it depends on the number of photons I'm shooting at the thing. So if I drive it with a harder laser, this coupling can be increased. So there's some just simple Heisenberg equations. They're called Heisenberg-Langevin equations because there's noise terms now. Okay, so whatever, they all couple. And I just want to highlight that there's damping in both systems. So this kappa means that photons can leak in and out of the cavity. And this gamma means that phonons can leak in and out of the mirror. And then there's some input fields. So these are the noise input, which this is in fact the thing you are shooting into and reading out of in the laser field. And this F is the phonon modes going in and out of the mirror. And so from that, you can derive some noise curve. That's how you make these SFF noise PSD plots I showed earlier. And okay, fine. So the point is the assumptions that go into this in a modern system are that the force input on the mirror is some thermal noise at some low temperature, say, or whatever you have, but no lower than 10 millikelvin usually. It's set by the temperature of the bath, not the device itself per se. So if you see a paper that says we have 5 microkelvin device, that means that they cool it down, but then it will heat according to a 10 millikelvin fridge.
But in this sense, I'm sorry to interrupt, but still, look, it looks like it's like a classical light wave, electromagnetic wave, rather than a collection of individual photons. And there is another noise associated with the fact that it is indeed collection of the photons, right? And my impression is that what you are writing does not include this. You know that it is square root of n when n is number of photons, for example. There is this noise. No, I mean, okay, even laser has distribution of photons, right? I mean, it's not, I mean, it is special type of distribution, right? But there is a width or whatever. And what you are talking is no, I agree that it is there, but I mean, this type of, but it's not exactly the same noise as, you know, kind of, and people do see this noise, you know, with this photo measurement or whatever. I mean, you know, photo multipliers, you know, that there I believe it is this type of noise which is important, for example, in particle physics, say.
Yeah, that's right. So that's incorporated here in the following way. So this is a subtlety of this notation. So this X in and Y in. So X and Y are a single cavity mode. The X in and Y in are the collection of all of the modes on top of this laser. So this is actually a 1D quantum field if you want. So this actually includes all of the photons.
Right, but where is the number of photons enters?
Yeah, so it's, I should have written it, but the correlate, so what you're gonna calculate is some correlation functions of the output. Yeah. Okay, and you assume correlation functions for the input to do that, and these are quantized as like x of t, x in of t, x in of t prime has an n, and n, you know, is this number of photons if you wish.
Okay, thank you.
Yeah. So because in the interest of time in a seminar, I don't want to actually go through and solve all these equations, although I could show you after. Let me show you how this noise is estimated. And so this is a very famous old paper by Carl Caves. What's the noise in an interferometer? This is this thing called the standard quantum limit. So what is this? So he says, suppose that the mirror is prepared in some wave packet. Let's say it's a Gaussian with some uncertainty delta x. And let's say it's, well, it is a Gaussian, so it's minimal uncertainty. It satisfies delta x delta p is h bar. So what happens if I measure the position of this thing? Okay, well, whatever happens, if it's a decent measurement, the uncertainty in the position should decrease. So the wave packet shrinks in, you know, position space. Okay, but if that happens, what has to happen is that the momentum uncertainty has to increase, right? Otherwise, I would violate Heisenberg uncertainty. Okay, so now I wait a second and I shoot in another photon and I measure position again. What's going to happen? Well, in the intervening period, the wave packet has spread, and it's spread by an amount that depends on the momentum uncertainty in the previous step. So if I make a very good position measurement in the first step, it's going to be harder to make a good position measurement in the second step because the wave function will have spread substantially. So there's some trade-off if you want to continuously monitor something with some resolution about how well you want to do it in the first time step versus the second time step. And if you optimize this problem, you wind up with some estimate for how well you can resolve the thing continuously. People call this the standard quantum limit. It's not a limit, okay, but that's what they called it, which gives you some order of magnitude estimate for how well you can resolve an object. And if you put in numbers for LIGO, so it's universal, it depends only on t, which is going to be the inverse frequency of the system in practice. It depends only on the frequency of the oscillator and the mass of the oscillator in h bar. So it's universal. This doesn't depend on how exactly you do all these measurements, but you will universally find a formula like this, no matter how you set it up. If you put in numbers for LIGO, this winds up being like your 10 to the negative 18 meter kind of resolution.
Look, but it looks like a natural unit in oscillator, right? Because it's h divided by omega m, right?
Exactly. Good. So exactly. So the other way of view, well, what this is it is the size of the vacuum fluctuations of the mirror. So this limit means I can resolve the vacuum fluctuation of the object. Exactly. So in that sense, it's also very universal. All right. So now in terms of what we are trying to do, what does this tell us? If you instead think of this as a measurement of momentum transfer into a device, which is what we're looking for, right? It's equivalent to the displacement. you can make the similar formula, and because of the interpretation we just heard, right, you can say this is saying I can resolve the input, I can resolve a momentum transfer to the device at the scale of the vacuum momentum fluctuations of the device. Okay, that's the standard quantum limit in momentum space. And it's, again, some universal formula. So just to give you a sense of what the numbers look like, for a nanogram oscillator at a kilohertz, this is a pretty small impulse, 600 keV. Okay. So imagine trying to see 600 keV kick to a nanogram. I mean, it's kind of incredible to think that you can do this, but in fact, this is done in practice all the time. Well, all the time means, in 4 labs, but it is done by multiple people now. So if you look at the milligram scale devices we had earlier, and you put in the numbers, what you find is that this measurement noise is about 1,000 to 10,000 times larger than the thermal noise in a well-isolated, dilution refrigerator kind of system. So I was saying what we need to do is get the measurement noise below the thermal noise. What this is saying is that, in fact, the measurement noise is pretty good bit higher than the thermal noise. So you have to do some real work. And this is sort of the real meat and trick with this scheme, is how are you going to actually do this? So this thing is called the standard quantum limit. It's not a limit. What it actually is it's how well you can do if you use Gaussian wave packets for the lasers, basically, and you couple in the naive way to position. So it's been known since Burginski and Galili in like 1975, a number of ways of evading this limit. And the 2 most known ones are squeezing. Okay, so you can prepare the light not in the ground state Gaussian. You can squeeze it in one quadrature, so that, and then only read out that quadrature. Okay, so this is used now all over the place. In fact, it's used very much in LIGO with about 2 orders of magnitude noise reduction now. And this is some kind of amazing thing. Like LIGO is running, the A-LIGO, they turned on the squeezing thing, and then the number of events went from like 3 a week to 12 a week or something. I mean, it's like the proof of this in practice is just amazing. So you can squeeze the light, you can get below this limit. This is how LIGO went from the 10 to the negative 18 to 10 to the negative 19 meter resolution. There's another way you can do this, which is called non-demolition measurement. So this is a little technical, but previously I was saying I couple the light to the position of the mirror. You can actually imagine some system where you couple to the momentum of the mirror. And for a slowly moving mirror, since the momentum variable, if you think of the mirror as just a free particle, if it's slow enough, the momentum variable will commute with the Hamiltonian, and you can show that will basically make the measurement in theory noiseless. Okay. That's not exactly true, but in paper, that's what it says.
But does it mean that you are in certain way kind of go into the system with a large mass, right? Where your quantum fluctuations are small, when you're doing this?
That's right.
So it's a kind of more and classical system, right? If it's effectively heavy mass. I'm not sure how to apply it to squeeze light, because it's not, I'm not sure what would be classical analog of squeeze light.
Well, so the light will be quantum mechanical. In some sense, this one other aspect of this limit is, and you can kind of see it from this picture. This is the problem is that the 2 variables you're using don't commute with each other, right? And so when that's somehow uniquely quantum mechanical.
No, of course, but okay, the only parameter which you can use, it's like effective mass of the system, right? The heavier the mass, the smaller these fluctuations are. And my impression is that when you're saying squeeze, it's effectively like kind of dealing with a more heavy particle, in certain sense. But I'm not sure whether I'm right. You see that because you cannot get something from nothing, right? So you should have something which governs this quantum fluctuation, making them smaller, right? And I'm using this mass as a kind of universal parameter to denote this. Let's
see. So with a heavy system, the typical problem is actually, well, one problem is that the thermal noise will become much larger. I don't know if this is answering your question. so let me give as a proof of principle LIGO, right? So LIGO is a 40 kilogram mass. And LIGO is now not only dominated by the quantum noise, but it's dominated by squeezed light suppressed quantum noise, right? And I mean, that's just the statement. So the LIGO mirror.
No, I agree that no, in certain sense, what I'm trying to ask about is that about squeeze light itself, because squeeze light itself, if I will try to represent it in the form of certain oscillator, I would say that this oscillator has a heavier mass than you know, non-squeeze light. No, okay, but maybe I'm not sure, because you see, because you cannot get you cannot change uncertainty relation. Right, what you can do, you can try to change relation between momentum and coordinate, right? I mean, this you can by mass.
Yeah, I don't have an intuition for this picture you have, I guess, of the squeezing, increasing the mass of the light. It's an interesting way of saying it. I can kind of imagine.
Okay, I'm sorry. No, I mass is no. I understand that it's not a mass of photon, right? But
it's true that you make the wave packet narrow, which is the same thing that would happen if you just had a a heavier system.
Yeah, right. It is my analogy, right?
So yeah, I'm not okay. So maybe we could talk about it a little more at the end. I mean, just in practice, it's okay. I mean, the thing that actually has been seen to be the ceiling on how well you can squeeze stuff is optical losses. It's actually nothing very fancy. It's just if the light goes in and out and you wind up losing some photons, and then the squeezing kind of gets degraded, and that's just what kills you in practice. That's what this 20 dB comes from. Yeah, unfortunately, it's nothing very cool. But maybe we can talk after it. Maybe I don't understand what actually you're getting at. I mean, are you suggesting that it shouldn't work, or?
No. I'm trying to have some kind of analogy, in kind of quantum mechanical system with less degrees of freedom. How I mean how squeezing could be represented. Just illustration for illustration, to not more.
Yeah, it's a good question. Let me see if I can think of a good analogy for you by the end of this. But okay, in interest of actually finishing on time, let me do the last few slides here. So the point here is just to say that there are methods to decrease the measurement noise, and in fact, they're not so far from what we need. Okay, so I'm saying I need 30 to 40 dB of noise reduction. You can achieve 20 plus a few. Okay, and that's with a sort of more brutal system like the LIGO, 4 kilometer interferometer. So it's not totally insane to think that you can get to this. That said, actually doing it is sort of the dominant challenge in this. So that's really the conclusion. The conclusion is, with current technology, well, with almost old school thing now, with it's interquantum limits systems, you're a few orders of magnitude too high. With more advanced things, you're still an order or two too high. There are known methods theoretically to get the noise to where it needs to be, but actually doing it needs development. It's something I spend a lot of my time on now. So the statement though is, if you can get the measurement noise down low enough, and if you can make enough sensors in this array, you can do this. It's not an impossible measurement task. And I want to emphasize that if you did this, then it's a deterministic thing. Gravity is deterministic. There's no, form factor for this. There's no probability. If the dark matter goes through, it will move the mirrors, and then you will detect it. That's the statement. So it's exciting in that sense. The real problem is that in addition to making very good sensors, you need a lot of them, right? Because I need them spaced at a millimeter, but I need it big enough to actually catch some of this stuff. So if I'm looking for Planck scale, that means I need a meter squared. So now we're talking, a 10 to the 6 to 10 to the 9 sensors, depending on how exactly you want to do this. Okay, so that's a little intimidating. I do want to say that this is not optimized at this point. These are still sort of order of magnitude in many axes here. So, do we really need a billion sensors? Maybe there's a smarter way to organize these things. But nevertheless, the real conclusion is just that this is very difficult, but not impossible. Okay. And it turns out that, there are people who are even crazier than me and who are willing to start building something like this. So to my great amazement, there's an effort to do this, to prototype this thing. So this is really Raphael Lang's brainchild. Raphael Lang's a xenon detector guy at Purdue. And has been organizing this collaboration to make a prototype. Okay, so this is how a prototype looks in the Zoom era. So this is some simulation that they've started doing. But the actual experimental goal as a first pass is to put about 100 sensors in a cube and see if you can read out, tracks of, say, I shoot a baseball through it, something, much heavier than a Planck mass. So the sensors themselves are fabricated at Purdue. It's this really beautiful architecture that Sunil Bhave came up with. So this is a 70 milligram drum head. It's coupled to a capacitive ring. It's exactly what I was suggesting earlier. So if something moves the drum head, it will deform the capacitor a little bit. And so then, some fields going through this ring resonator here, the frequency will be slightly shifted and you can read it out just like the light in LIGO. These are fabricated on a chip, so you can just make tons of these in theory. All the readout is on this chip and everything. So this is within a year-ish, 2 years maybe goal, just to build a little prototype with 100 of these things and see what you can do with it. So this is going to be a far cry from doing the full gravitational detection. This is more of an exercise to just see what it would be like to build an optomechanical array, which actually has many other, beyond dark matter detection, has a lot of interest in this. Within dark matter detection, I want to finish, because I think Jen would be mad if I didn't do this. I want to say that there are other things you can do with this on a much more immediate time scale. In fact, on this immediate time scale. Okay, there's many other signals you can look for, and we certainly don't have an exhaustive list of everything. But one that we have thought about, and this is really Jen's idea, was to look for some ultralight dark matter fields. So if you live in the dark matter world, I'm sure you've heard of this. If dark matter is very light, totally opposite end of the spectrum, right? Sub-EV mass, then it will be some kind of coherent oscillating field filling up your lab. And if it couples to these mechanical sensors, you can try to look for it. So I'm giving an example here where the dark matter is some gauge boson that couples to neutron number. And what this will do is it'll cause a persistent acceleration on all of the devices in the array. And this is actually sort of a much easier thing to look for, in the sense that this is what people already do with these kinds of devices. They're just accelerometers, and they're roughly monochromatic accelerometers. So they look for a slight acceleration, all at the same frequency. Fantastic. So just to show how sort of powerful this is, so this is a plot of the reach for these devices. So this is a plot, I think for you guys, it's easier to look on the top. So this is as a scan of dark matter mass for this ultralight field versus its coupling to neutrons. All this blue stuff on the top is ruled out. And with a day search with one of these, well, 2 of these devices, for technical reasons, you need 2, you get an exclusion curve that looks like this green line. So forget this blue and yellow line, this for accelerometer people. The green line is just what is this architecture supposed to be capable of if you put it in a dill fridge and it works right, TBD. You can really start carving out a non-trivial part of this parameter space pretty much immediately. So this curve only gets better with 100 sensors and all this fancy quantum stuff. So it's really, there's a whole sort of program implied by this plot, which is you start building these things and you just start carving out this parameter space.
Is it a broadband search or it's a resonance search that you're thinking?
Yeah, so good. So the dark lie in this plot is this is a sort of a resonant-ish search. So the way this curve is constructed is actually
it's time to scan, no?
yeah. So it's resonant, but the bandwidth can be tuned. So it's not a perfect resonance like the axions. You can make a. So I think we constructed this plot, if I remember correctly, by you, at every order of magnitude, you have to do a search, if that makes sense.
So fast scan.
So it's a relatively fast, but it's not a, it's not like you turn it on for a day. Sorry, so this plot has integration time of a day per band.
Mhm.
Yeah. That said, if you do a true resonance search, of course they can look better, but okay. Good. The other thing to say is that, building one of these is a hell of a lot easier than building an Axion cavity. So in fact, like, they're fabricated on chip, like I said. And so you can imagine fabricating them with slightly different frequencies and doing a kind of quasi broadband search with many multiplex devices that way, which is an interesting approach. All right, so I'll end with, this is, sorry, just a true advertisement. So there's a number of other things. So this sort of work has spawned a lot of interest by the experimentalists in particular. So I just flagged that there's been a number of experiments already started that are not what I was talking about. But so Dave Moore at Yale has his group with these little levitated dielectric beads, which are just, this is the mirror now, basically. And they've looked for some dark matter, some composite dark matter candidates with that. There's been a lot of interest by these guys. These are experimentalists at Delaware and Arizona to make a vibrating membrane. So this is a different architecture, but now this membrane is the mirror that can move, and this bottom piece is the fixed mirror, and you can look for these ultralight models there. And so they really are thinking of this as a more resonance search. There's a number of other experiments, and I'll give a reference for a review. But I just, yes?
B minus L refers to, baryonic leptonic charge, or notation B minus L refers to what? When you wrote G by B minus L?
So my understanding of this is just you assume that there's a B minus L charge, and then you gauge the conservation law, right? So that there's
so there's a new gauge field associated with B minus L?
Yeah, that's right.
Okay.
My understanding is this thing is anomaly free in the standard model, so that's why people like it.
Neutrinos are Dirac as well.
Yeah, so I for a detector person, I just like this because I can write down this model, and you can think of things that couple to the electrons in these devices. That's something people have started thinking about now, and okay, but the limits tend to all look similar, and that's because they're set by vacuum fluctuations. They're very universal looking formulas. Okay, so there's a bunch of stuff going on. We're gonna have a workshop. We had a workshop a year ago about this optomechanics and dark matter, and if people are interested in this, I can advertise. This is an open half-a-day update on all the experiments that's happening, and I think you'll have my slides, so this is easy to find. And if anybody wants to talk, send me an email. So I'll end with some just open questions. So this is what we're doing now. So as I think I've emphasized, the key thing from the detector side is how exactly do you make the protocol to get 30 dB noise reduction, specifically tailored to these impulses? So this is a really interesting question in just quantum measurement theory. There's another question, which is this thermal noise estimate we make really accurate, and is it really accurate from 0 to 10 megahertz? A variant on that question is, are there smarter ways to avoid it than just putting everything in a dill fridge? If you levitate it, if you drop it, can I error correct it? Okay. A much more gnarly question that a lot of people are working on is how exactly do you do this data processing? So, I have 100 sensors, I read out their forces in time series at like a gigahertz. How the hell do I do a matched filter search through that mess? Okay, that's a hard question. A more theoretical question that I think is very interesting, and I'm trying to pursue this a bit now, is there a smarter way to do this than reading out every sensor individually? So for example, if you read them out through one laser that pings off of all of the mirrors, you can imagine, in fact, averaging out some noise that way at the level of the amplitude in the mirror. So this is called Heisenberg scaling. And you can imagine actually getting better sensitivities if you could do what's called a correlated readout. But how exactly you would do this is a whole, it's a research program to figure this out, really. Another thing that's interesting is, what about the phonons? So beyond the center of mass of the mirror, can you do anything with those modes? Oops. Okay. And so this is just a list. And then, you know, the thing that I should have also added is pheno. I mean, what signals can this stuff look for? So heavy dark matter, great. Very ultralight dark matter, great. I mean, there must be some other stuff in the middle. And so, you know, it's interesting to think what you can do. These are, at their heart, this would just be the best accelerometer ever constructed. So anything that can make an acceleration signal, you can contemplate looking for or setting a bound with this thing. So it'd be interesting to start, you know, having a longer list of candidates. So yeah, that's all. So thanks very much.
Yeah, thanks, Dan. That was very interesting talk. So virtual applause is here. Do you have any questions?
I just want to clarify one thing that actually related to what Maxime asked about whether we are doing a narrowband resonance search or a broadband search. So then I'll go back a few slides where you show like David, the next slide. Yeah, so you see on the bottom right plot, that is a very sharp peak. That is a typical response function of a resonance search, right? Where that's why you have to do a very fine scan to achieve some good sensitivity over a large range. However, for the ultralight search in Dan and I are envisioning, we are not limited. We're in this range. We're not limited by the short noise on resonance, and so our response function moves like degrades much slower when I move away from the resonant frequency. And that's why we only need like 1 step per decade in frequency just to achieve a relatively good curve. In that sense, every step is a broadband search for us because we're not relying on the sharp resonance of the fundamental frequency of the device. Yeah, just to answer Maxime's question.
So I have 2 questions. Why did you pick B-SL? Is it so? Would this apply to dark photons or no? Just because it's screened, I guess, because of
Yeah, so the dark photon version is interesting. I think Jen's been bugging me to work on this for like 2 years. I mean, I think the short answer is we just haven't worked it out. So these devices I'm showing are typically electrically neutral, in fact, of very high accuracy. However, you can imagine charged versions of them, and they may in fact be very good. My understanding is that DM radio is kind of like this. Like there's some, but anyway, let me not guess what exactly DM radio does.
But look, by definition of words, dark photon should interact with dark matter, right?
No, we're talking about dark photon, dark matter. The dark matter itself is a vector field that kinetically mix with our photon. So it's coupled.
I'm just trying to kid that in this way everything which is dark interacts between itself, right?
Yeah.
Darkness to darkness.
Yeah. Right.
No, I'm not serious about this, but I still wonder that imagine that you will be able to measure, this kind of particle. My impression is that in terms of particle physics, you are talking about extremely heavy stuff, right? Or I am wrong?
For the gravitational thing.
No, when you are saying that it is milligram or whatever, what you are observing if I will try to realize it as a particle, right? Then it's kind of tremendously heavy particle, or I'm wrong.
No, that's right. I mean, that's a whole other interesting question. So what the hell can be a Planck mass-ish dark matter candidate?
Yeah, because
because in this way, you see that if you believe that it's enough evidence already to existence of heavy of dark matter, then you can say that okay, existence is established. However, when you're trying to find out this elementary object, then for example, how you differentiate your discovered particle from what people discuss like kind of black holes, for example, or that because we are still interested in physics of what it could be dark matter stuff, right?
Well, I guess I would say
Arkady, black holes in that mass range will evaporate.
This kind of heavy mass maybe not enough for us, right? And it's not sufficient, to say that it's something very heavy.
black holes in that mass range may
I mean,
evaporate quickly, right?
Well, this depends. I guess you can imagine charging them under some large ZN group, and there are ways of stabilizing them, I guess. I mean, I agree that I don't consider it so likely. Let me say that if suppose we did this and we actually found some junk flying through and it was a Planck mass, I mean, who cares what else you found out about it, right? You can make another experiment. It would be such a crazy thing to, you know.
No, but it still would be interesting to put in framework of some understanding of physics of the dark matter, right? That in this
Arkady,
way-
what can happen is agglomeration, right, of stuff, right, of many particles.
Agglomeration.
Yeah, for example, people discuss this Coleman stuff, cue balls, right? So if you add some global symmetry and there is a distributed charge, right, then the bosons can sort of under certain self interaction, it would be preferable to form blobs of matter rather than individual particles.
But is there a fundamental candidate? Is there a model with a fundamental candidate, like an elementary particle Planck mass that's stable? Do you have is there a favorite model or anything like that?
So I asked John March Russell once about this.
Okay.
You know, someone who I thought would be a good person to ask about crazy stuff that could possibly exist. And he said, you know, imagine that you had a string theory model and there's a long throat and you can stabilize some KK modes at the bottom of the throat and you can tune them to be Planck mass, for example. So I think I took this as a proof of principle that you can definitely cook up stuff. I think I personally.
Why doesn't that decay? I don't understand. If it's a KK state, it decays.
Yeah, you'd have to ask John.
So sorry, but Tony, are you asking a good model in a sense of why it's stable or why we have the radical abundance of ultra heavy? Agree with our
both. I mean, look, I'm all for these pushing the limit and trying to find these particles. And as Dan says, if you found something, it would be fantastic. But I was just wondering whether there's also just some model that someone has built, or maybe there's a potential to build some model that could kind of realize some, besides accumulating a lot of mass like Maxime was saying. I was just thinking more just something like more elementary. Is there a model like that? Would be interesting. But I'm not saying that, but you should still look for these things. But I was just wondering.
Yeah, but from my naive point of view, one can easily write down a stable particle who have a heavy mass. So long as that mass term don't break our standard model gauge symmetries. Question is more on how do we achieve the radical abundance there. Then there's various ultra heavy dark matter production mechanism from so many different mechanisms that I'm not expert on. Colliding walls or radiation from black hole, something like that. I don't know.
But is there a generic example that's just very simple to state and write down? That's kind of what I was thinking of. Nothing. Yeah.
I think the answer is roughly no. I think the simplest thing I have actually sort of understood. Maxime said something about this. They're these soliton solutions. So Yang, I'm trying to remember who did this. Yang Bai did this. But even there, the mass is tunable in some sense. So, there's a question of can you make a natural Planck mass E candidate? And that I think is an interesting question. Which
that's what I was getting at. Yeah, exactly. Yeah, I was just curious. Yeah.
I think Yang Bai was in the audience in the beginning part of your talk. Yeah, he should have commented. Can I ask another question? But actually more to earlier comment by Maxime. I was surprised though when he tried to make connection of the LIGO massive frequency to the dark matter mass. Right? LIGO, in my point of view, the LIGO has its best sensitivity band, which is about 100 hertz, right? That's where its noise is the lowest. Then they are just sensitive to yeah. In the ultralight mode, it sends to dark matter in that band. In the ultra heavy mode, I think there's no frequency at all. They are really limited by how frequent by the flux and also the force sensing threshold, because I have to take the mirror in an appreciable amount which is an ultra heavy mirror to make it detectable. I don't know if Maxim are still here.
No, I still think that their best sensitivity is the characteristic frequency is you take the velocity of dark matter and you divide by the length of the arm, right? Because if you're too far away from, then you affect both arms the same way, right? And if you do that, then you get you just get to the typical frequency that the perturbance that this dark matter creates is 100 hertz, right? The Fourier transform of your signal would be 100 hertz. However, to make it detectable, you need to make it into tens or I forgot, hundreds of kilos or something like that, which makes these occurrences extremely rare. That's all.
Sure.
But the frequency is fixed in that sense.
Okay. In other words, you just want to avoid double appearance in both arms.
Well, if you are passing way too far, right? You pull on both masses the same way, and then there is no appearance, right, of the signal. You need some sort of a distance. The impact parameters say comparable to the arm's length, then it's clear that you will have a differential effect, right?
Maxim, I'm trying to notice that to be more convincing about dark matter, you are making you are making dark yourself.
Well, that's because I'm making a real, not dark lunch. That's why, right?
Okay. Now I'm enlightening you.
Yeah. But then you move on to these slides on purpose, right? So are you trying to say about our broadband?
No, I was just trying to say, I think I agree with Maxim's estimate. He's just, in my language, saying that he's estimating the impact parameters at the size of the device, same as we are, really.
Yeah.
Okay, I see. Okay, but on the same slide, actually, it also shows that we are a broadband search for the ultralight mode, because our noise level, if I may annotate, this is our noise level for a single run, right? And we are not limited by this resonance noise floor, right? If we were not limited by this, we are ultra narrow band search. But for a single run, we already, we have best sensitivity in this line, but we have comparable sensitivity, in the neighboring frequencies. That's why we are allowed for, big step size for the search. So in essence, we're actually doing a broadband search. Just to say that. Okay, but I think I forgot we are at LIGO. We are doing a differential measurement. Then I have to do this math as Maxim just said. And okay, I don't want I don't want to occupy all the questions that other people ask. Yeah.
So if I'm being very optimistic and you have several events like this, can you start measuring the dark matter velocity distribution in some way?
Yeah, so you would know its directional distribution for sure. Actually getting the velocity out of it in principle, yeah. So as long as you're sampling fast enough, you know, because you're saying the frequency. So in other words, the frequency is 100 megahertz. So if you're sampling at a gigahertz, in theory, yeah. In actual practice, it's TBD. It's a pretty challenging data processing thing. So in particular, whether, you know, how you compress the data and stuff matters. So actually, these guys in Purdue and Raphael's group are trying to do this right now, just to simulate this. So you have a box, you resolve everything in 100 megahertz. Can I actually resolve a 200 kilometer versus 250 kilometers per second velocity? I think the answer tentatively actually looks like yes, according to them, but yeah, it's a detailed question.
Okay.
Yeah.
And is there any advantage? So I don't really have, it's kind of a pseudo question, but if I have a different scaling in radius, so I'm not looking for some long range 1/r squared, but I have some, you know, higher power of R in the denominator. Is this better or worse for you? Because you can imagine a smaller impact parameter.
That's a very good question. Yeah, I mean, it could be better for sure, for the exactly as you say.
Yeah.
I don't personally know a good such model. I mean, so you can imagine taking all of this stuff and scaling it to smaller systems and looking for, say, dipole coupled stuff to mechanical dipoles. And I guess then you'd have an example of something like that.
Yeah, I mean, I don't really have a very good reason, but I'm just kind of thinking of like some long range force examples that would scale like 1/r⁵, for example. This would be.
You
like
can think about it. So the one thing that sort of underlies all of this is that the force needs to be coherent on the scale of the device. So there's some trade-off here, right? So you know what I mean? So I need to move the whole device in one way. So as long as the range is long enough that that's going to be true, but you get close, maybe you can win. Yeah, I don't have a good quick answer.
Okay. What's your typical separation then?
We picked millimeter because of all these gravity parameters, but you know, all of this stuff in some way is like super universal. So you can just imagine masses at pretty arbitrary spacings, as long as it's they're spaced 10 times longer than the solid density would suggest. And then you're going to have just an array of isolate systems. So you can imagine doing this, for example, with ions, if you want to go to an extreme other limit. So, you know, if you have some example, you know, there's definitely like an impulse sensing thing you can imagine doing at pretty arbitrary scales. Let's say down to a micron.
Interesting.
So sorry, you said that you can get down to distances which are of order a micron separation. That's what you said?
Well, with a very different system. So not with these milligram things.
Oh, okay.
So with the milligram things, I think 100 microns is really starting to push difficulty. I mean, they're in Haute-Vache land and stuff. What I'm saying is that, you know, you can imagine using trapped ions in a quantum computer. Those are separated by a micron, and those could be little sensors if you want.
No, because I was just going to say that if you're at sub-micron, then we know that the gravitational force law is not necessarily 1/r².
Good. So this is actually the original motivation for, I don't know if you know Dave, but that was...
No, I'm just thinking of the Adelberger group in Seattle.
Exactly.
Yeah.
So exactly. So they're limited to about 50 micron, and that's because of Casimir forces between the two masses. So one way of phrasing these ultralight searches is you're actually doing a fifth force search, but the source is no longer your second mass; it's the dark matter.
Yeah, I was thinking of that too. Yeah, exactly. Yeah, it's not another mass. That's right. Yeah.
But one reason Dave developed this system is specifically because with these small masses, you can get them closer than 50 micron, and you can actually suppress the Casimir a bit better. So one of his goals is to get, you know, a 10 micron limit on the fifth force, for example.
Oh, I see. Yeah. Very nice. Yeah.
Any other questions?
Yeah. Dan, can you go to the slide you talk about the squeezing light? I really just have some naive question. I somewhat feel surprised to see LIGO is able to reduce the quantum measurement noise by 2 orders of magnitude just by squeezing light. To my naive understanding, right, as you educated me that from a standard like distribution of phase and amplitudes, I'm interested in particular dimensions, so I can squeeze the uncertainty in that dimension and just to achieve better sensitivity. But intuitively, that's a very how do I say? That's a helpful technique, but usually only reduce noise level by a factor of a few dB. Do we really achieve like 20 dB reduction just by squeezing?
So I think the actual statement is they produce squeezed light, which is squeezed at 20 dB, meaning that the width of the wave packet of the probe field is squeezed by a factor of 100. The actual reduction in the noise in the readout is not as good. I think it's about 12 or something, if I remember the number. And the reason it's not is because of optical loss. But it's still a sort of on the order of, there are orders of magnitude reduction. There is an order, let's say, of order of reduction in the sensitivity of the actual gravitational wave output.
And I was also confused about your statement about the second non-demolition. You were saying that theoretically the limit is, there's no limit on the amount of noise removal you can do with that. Can you explain like why there's no limit?
Do I have this? Yeah. So this is how that would work. So if you sort of grokked my earlier cartoon about the standard quantum limit, about I do a position measurement, it moves the wave packet size that causes wave packet dispersion and so forth. If you measure the momentum, this is not the same picture anymore. So now in momentum space, say you measure momentum, okay, so the momentum space width will decrease. However, I'm assuming a slow oscillator, and I'm going to measure momentum in the next step. So in fact, the variance, P commutes with the Hamiltonian. So the variance of P is a constant, right, in time. It won't change, right? So therefore, in the next time step, the thing will still have this reduced momentum space variance, and then I can measure it again, reduce the momentum space variance, measure it again, and just continuously do this.
Well, I understand, but it seems all the magic is because my measurement of momentum here, you think that is decoupled from my position determination, right? But in the real system, how do I measure momentum without any dependence on position?
Yeah, I mean, we have, I don't know, 2 students working on, I mean, this is a whole thing. There isn't really a good proposal for this. It's a beautiful measurement theory problem. How do I actually couple to the momentum quantum mechanically?
So in some sense, it's still in theory. Right.
Yeah. So there have been a couple of proposals, but I mean, like the thing we're pursuing, for example, is imagine you had E and M, right? Then there's a coupling. The coupling is J dot A, and the J, if you think of that as the thing you're going to measure, right? It's got the charge times its velocity. So roughly speaking, that J dot A term has a momentum of a charge, and you can imagine coupling to that through the optical field, which is the A. And so in that sense, it would be a direct P to optical field coupling. So how exactly you implement that is like a whole thing, but that's an example of an idea. Right, as opposed to the mirror where you measure the position because the light has a boundary condition that just changes the phase shift at the position.
Okay.
Yeah, so I wanted to comment on the question about solitons, but there was a problem with the microphone. So no, I just wanted to say that, yeah, I mean, you can take a heavy soliton like a cue ball with large mass. In general, there's no problem with that, but in general, it would also have large size, because in general, the size of cue ball scales as, its mass to some power. So, and if you try to cook up some dense configuration, which is very narrow and very heavy, then most probably it will just blow up immediately, decay into smaller cue balls. So yeah, so I don't know of any explicit model with a small and heavy solitons.
So yeah, very interesting actually. So if they were big, but not like bigger than the whole apparatus, you can still look for them. So then instead of doing a track search, you do sort of like a fat track search, right? You look for the one, but then I guess the impact parameter is effectively larger, so maybe you won't be sensitive enough. That's interesting. I hadn't heard that they were big like that. But you could imagine hunting for those with something like this, as long as they were within the detector volume. Just to say, there's nothing fundamentally forcing you to look at narrow tracks. You can look at more collective motions.
Yeah. No, I agree. Yeah.
But
Yeah, that would be interesting.
It'd be interesting to sort of make a real model and figure out how well you can do that.
I mean, also you can make, composite systems containing many between each other and so on. So that's
I think that's what most of us kind of have.
I mean, people used to consider them as, people used to consider them as, there were attempts to consider them as elementary particles, right? I mean, solitons, not necessarily cuboids, just in general solitons many decades ago, right? Some, classical configurations. So now they're viewed as mostly as, some background, at the level of background fields, right? So some classical configuration, but not really quantum, really classical object. So these small quantum fluctuations are not are negligible. So in general, if it's cuboid, in general contains many particles, so it's a classical object.
Any more
Okay.
questions?
I like classical objects. Detecting classical things is just fine. Sorry.
Maybe I'll stop recording.